Okay, so let's solve some more exercises, and this time, next to giving like techniques of solutions, I'm also going to explain how to write a nice, well-written solution for each one of these exercises. We have 3 of them. So yeah, let's get started. So the first one is just a linear system. So let's try Gauss-Jordan elimination. The new thing here, the like strange thing, is that it's not actually just one system, but a family of systems which depend on this parameter, which lies in the real numbers. So we'll have to be careful and study the solutions depending on this parameter. So we start. We see what we can what we can get. Okay, so trying to do Gauss-Jordan elimination. We get this matrix, and we know that we can do some allowed moves to transform it without changing the set of solutions. Namely, for example, we can multiply this second row by -1, thus getting this. Okay, and then we can replace this second line with the sum of the two rows. Sorry. So let's do this. You get the first row is the same, but here we do the sum, so we get 1 plus t and -1. Okay. Here comes the tricky part. So we have a 1 here, which is good. We would like to have a 1 here. In principle, we would like to divide by 1 plus t, but we can't do this if 1 plus t is 0. So we have to make an assumption here. It's a very important thing to not to forget. So assuming this is not 0, then you can divide, and you get this. This is 1, and this is finally. Okay, now we can easily find solutions. Namely, this is now the system is kind of easy. So we can substitute. And okay, and then you can find the which is yes, and this is it, and this is it. Let me just yes, okay, fine. But this is not over, because we made this assumption here, but we have to know what are the solutions for each t. So in this case, we have t different from -1, but what happens if t is equal to -1? Well, you substitute here, and you get so you know that when you have a situation like this, after doing the Gauss-Jordan elimination, then this implies that, well, the system has no solutions, because, well, while searching for them, you would get something like an identity between 0 and -1, which is not possible. So this is a contradiction. I mean, that 0 is equal to -1 is a contradiction. So in this case, we know that we have no solutions. Okay, and this is it for the first exercise. Let's go on and do the second one. But don't forget that after solving all these exercises, we'll have to rewrite these solutions in a very nice and properly written fashion. So let's go on. We're just like, if you want, we're like trying to simulate a situation where you are given these exercises, say in an exam, and first you like find the solutions. But I mean, here these are just notes. This is like a draft, and then, well, you decide to go on and make other drafts, and then at some point you'll have to rewrite the solutions nicely so that they are readable. And people who want to read them find something which is nice to read, which is well written, and so on. So let's look at the second one. This is about using matrices. This is kind of interesting. This is about using matrices to process information. So in this case, we have a company which wants to produce these goods, these and these, and to do so, it has raw materials, and the production is given by this data. So in order to produce, for example, one plastic pipe, you need these raw materials. Well, not really raw if you want, but let's say materials. To produce one roll of wire, you need these materials, and to produce one copper pipe, you need these materials. And I'm asking you, the exercise asks you to calculate the total amount of materials needed to produce these goods, and also to determine the costs after you know the costs of these materials. Okay, so how do we do this? Well, I think a way of interpreting a matrix, and also matrix multiplication, I'm going to write here, is by thinking that, well, here above in the columns you have an input, and here there's an output. And also, if you have another matrix, you can, and the output here agrees with some other input here, and I don't know, here you have something else. Then by doing by doing the matrix multiplication, you get something like this, where the orange input and output cancel out, and you get a processed data somehow. But yeah, perhaps this is not so clear, but with this example, with this exercise, it's going to become clear. So the key data is this one. So this gives really the processing of materials into components. into goods, this plastic pipe and this roll of wire, this copper pipe. So this is now clear that the materials are the input, whereas the components, the goods, the produced goods, are the output. So you can say here as an output, for example, this row we have one plastic pipe. Here we have one, what is it, roll of wire, and one copper pipe here. Whereas here you have as an input the raw materials. So this is kilograms of plastic. Here you have kilos of copper, and here you have liters of gasoline. And you know that to make one plastic pipe, you need 2 kilo of plastic and 0.3 liters of gasoline, no copper. So this is this 2 kilo? This nothing, and this is 0.3. And to make one roll of wire, you need 0.5 plastic, 0.5 copper, 0.1 gasoline. And to make one copper pipe, you need 3 kilo copper, nothing here for plastic, and gasoline 0.4. Okay. And this is it. This is our processing matrix. And okay, what about the other data? So we have an expected production data. So what is this? So here we have an output, and now we want the output to be this. So how can we interpret this? And then the exercise asks to calculate the total amount of materials. So somehow what we want is to know the materials, so things here, such that we have a specified production output. But yes, recalling this thing, we are going to do we're going to need to do a matrix multiplication. But yeah, you see that things that come here have to agree with something here. So what can I do? What if I just write my expected production this way? So is plastic pipes, rolls of wire, and copper pipes, 680, okay? So this is what? Plastic pipes, rolls of wire, copper pipes. And let's say that this is the final production output. Okay, so you see that this row agrees with this. So we can do matrix multiplication, and what happens if I do this? Well, oh, sorry, okay. If I multiply here, so here you have the orange, go here. These are the plastic pipes, rolls of wire, and copper pipes. And here you have the raw materials. And here you have your final output. Okay. So when you multiply this, following this, like this suggestion, this like interpretation I gave you, what you have is that you'll get some row vector here. I don't know what. You multiply this to this, and then to this, and then to this. So in the end, you'll get some row vector with some numbers here. You can calculate. I want to do this. It's not really essential. But the point here is that you have, this is going to be kilos of plastic. This is going to be kilos of copper. And this is going to be liters of gasoline needed for the final output I want expressed by these numbers. So this is what I want as a final output for each component. And by doing this multiplication, the orange part, so the materials, if you want, cancel out. What remains is just the final output and the materials. So in the end, this is the materials I'm going to need to obtain this, to get this production output. And finally, the costs. But now we should have somehow learned the tricks. So the costs, can I interpret it as a like input-output matrix? Well, yes. Namely, here in input, I have euros. Let me just find another. Here, euros. And there's an output here. You get the material. So this is kilo plastic, again, kilo copper, and liter gasoline. So, and we know what is it? What this is? So 100 euro for 1 kilo, and we get 1 kilo. 210 euro for 1 kilo copper, and for gasoline just 50 euro. Okay. So now, to compute the costs of the total production, what I should do, if you see here, this now agrees with this. And then what if I do just this multiplication, so this A, B, C times this 100, 250. This is the euro, and this is the final output I want. And here you have the red things which agree. So if I do this, which is going to be, this is like 100A plus 50C. This is going to be the total cost. And if you want, I mean, this is just a number, but if you can also interpret it as like a 1-by-1 matrix, of course. So you can view it as like some number here, and this is going to be euro for the total production costs. Oh, okay, sorry, this is not euros, this is the complex numbers, okay. Okay, and this is it. This is how you solve this kind of exercises, by doing clever matrix multiplications, thinking of matrices as like things with an input and an output. Okay, and this is it for the second exercise. This is how you solve it. And let's go on to the third and final. And this is a little more theoretical. So here I'm going to read this out. So recall that a square metric C is symmetric if it is equal to its transpose. And we have to say whether the following claims are true or false and to justify the answer. Okay. So just a few words here. So if these are, let's say, these are claims, and You don't know if they are true or false. You can have some like intuition, you can try to make attempts and so on, but the important thing is that if you feel that things are going to be true, then you have to give a proof. So if it says if A is any square matrix, then this holds. And then you have to fix an arbitrary square matrix and prove this claim. If instead you have the feeling that the claim is false, then it's different. If you want to check to prove that this is false, then what you have to do is to prove that not all square matrices satisfy this. So there is some square matrix such that this does not hold. So, in simpler words, what you have to do is to find a counterexample. And okay, let's see. So, here, well, to test, to do a test whether this is going to be true or false, well, you look at this, you look at the definition, but you should remember here, since symmetric means that it's equal to its transpose, it's going to be important to remember some properties of the transposition operation. So remember, and this is something that when you study and when you do exercises, then, well, if you studied properly, then you see that you have an exercise which involves matrix transposition. Then the first thing you should do in your mind is, yes, just recall the properties of transposition and see. So, for example, we recall that for any square matrix, actually for any matrix, the transposition is like linear. So if you transpose a sum of a matrix, if you transpose the sum of two matrices, then you get the sum of the transpose, the sum of the transpose matrices. Whereas for products, it's a little have to be a little more careful. But you can't write that the product, the transpose of the product is the product of the transpose, but still, if you exchange, then this holds. So the transpose of the product is the product of the transpose, but yeah, with switched members. Okay. So, and yeah, if you want the transpose of the identity, well, there are some other properties, but let's say that perhaps these are going to be useful. This is not really, but this is going to be useful because, well, the first question involves a sum, the second involves a product, and this also involves, like, not really a sum, but, well, if you have any linearity also means this, of course. So in particular, if you have minus C transpose, then it's minus C transpose. Okay, so let's see. Let's just make an attempt. So for the first one, I fix A, and let's see. What if I do the transpose of this A plus A transpose? This is what I want to check, right? I mean, symmetric means that the matrix is equal to its transpose. Okay, so I'm going to compute its transpose and see if it works out or not. Okay, so this is going to be A transpose plus A transpose again transpose, and now I call another property which I forgot to mention earlier. Namely, that I put it here, that if you do the transpose 2 times, then I get back C. So that taking the transpose is like an involution. if you do the transpose of the transpose, then you get back what you had. Okay. And so this is ATR plus A. But fortunately, the sum of matrices is commutative. So this is going to be again A plus A transpose. And you see that this is equal to this. Well, this is equal to this. So it's equal to its transpose. So it's symmetric. And A was arbitrary, so this is actually a proof. We're going to write this better later, but then let's go on. What about the product? Let's do this. Transpose again. You have to be careful here, because by transposing the product like switches members, so this is here you have A transpose, again transpose, and then you have A transpose. But then you know that double transpose is again the same matrix. So you get back A times A transpose. So here and here. And this actually, since A is again arbitrary, this is a proof that actually this is symmetric. This A times A transpose. Just be careful here. If it's confusing, then call this like C and D, and this you see that this is D transpose and this is C transpose. So we are applying the formula correctly. Okay, fine. As for the third one, let's try naively. Let's again fix A, and let's see. What if I transpose this? Well, this is, I use again linearity of the transposition, so I get A transpose minus A double transpose, so A transpose minus A, which doesn't look really like A minus A transpose. So here I start to suspect it's going to be false. But it's not over. I mean, this is not a proof that the third claim is false. This is just a hint, namely that when you try to do like to transpose, you don't find the matrix back, but you find something which doesn't look like the original one. But this is not a proof, because here to give a proof that this claim is false, we have to find an explicit counterexample. So we have to find A such that actually A minus ATR is different from A minus ATR. Okay. And how can I do this? Well, I can think a little bit. For example, what if I try some easy matrices? For example, the identity matrix. Well, unfortunately, the identity matrix is equal to its transpose. So if I do this if I do identity minus identity transpose, I get 0, which is also the transpose of so this is not a counterexample, and you see that for some matrices it can happen that even this is going to be symmetric. But the point is that the claim tells A is any square matrix, and perhaps this is not true. So what if I try to find some more complicated matrix? So for example, let's take just a 2 times 2 matrix. I mean, here the claim gives any square matrix. But since we don't specify the dimension, then it can be any dimension. So the counterexample can be in any dimension, the one you prefer. And so let's see. What if I take A this? Well, even easier. So this. What is the transpose? It's like this. Okay. What is A minus A transpose? Well, it's 0, 1. This is a minus 1. This is not symmetric. So if I put some non-zero thing in any place which is not diagonal, then I'm able to get a counterexample. So this is going to be a good counterexample. This is a matrix such that this difference is not symmetric, because I mean, if you want the transpose of this, the transpose of this would be, that would be 0, minus 1, 1, 0, which is not this one. Okay, so we actually made it. It seems we managed to solve our exercises, but it's not over yet. We have to write solutions. This is very important. This is very important, and this is what we are going to do. So let's go back. So if you want, just imagine you're doing your exam, and you're happy because it seems that you managed to do all your exercises quite good. But it's not over. This is not a nice solution. It's like a correct draft if you want, but this is not a solution. So we are going here. If I can add a page here. We're here. Okay. I hope it's, yeah, okay. So let's use this new blank page to write a nice solution of the first exercise. We'll have to look back to the solution at some point, just to like rewrite things. And of course also this rewriting job is very useful, because if you happen to do an error which you're not aware of while arguing, perhaps like in a drafty way, then by rewriting stuff nicely, it's more likely that you will find this error, this issue. So, well, whenever you rewrite things, trying to be like very detailed and very clear, then it's easier for you to spot your errors if there are some. So let's see. We have this system, and we have to solve it. So I'm going to be very detailed. We are going. So we're going to solve the given system using Gauss-Jordan elimination. We consider the following matrix. Okay, and this is just this one. Okay, if we want just give a name, it's not really 1t 1 minus 1. Okay, so, and let's like be very detailed. Every passage you do, you justify it in a very detailed way. So the first if you want, let me refer to the rows as 1 and 2 like this. We every step is an allowed move of the Gauss-Jordan elimination. So we get this, we write it here, minus 1, 1, minus 2, 1. Second step, and this is again the first and the second row again. We're now at the second step, so we replace true the second row here with, and this is another allowed step, and you get this. Okay. Okay, fine. So the third step, we assume, this is very important, this is actually the crucial step, we assume that 1 plus t is different from 0. And if you want, divide 2 by second row by 1 plus t, thus getting this. Okay, let's just check that we are doing we're doing things correctly with respect to our draft, and it seems fine. Okay, we assume this, and now we have divided. We are like here. Okay. So in this case, we get the equivalent system as follows. So this is x plus ty equal to 1. Okay, and yeah, y is equal to minus 1, this. And here we substitute y and find, let's go here, y is equal to this is x plus t. So here, is this correct? No, it's not correct. There's a minus here. That was a mistake. Just be careful and check everything properly, and perhaps it's better if I have space so I can write things a little more. Minus. Okay. So from this we just compute. Don't have to write down that you compute. It's like it's clear. And then okay. Okay. So we conclude that if 1 plus t is different from 0, namely t different from -1, then you see that we are asked to determine the set Vt of solutions. Then Vt is given by what is it? If you want to write this as a vector, okay. You can also write just this. It's considered to be like standard to express solutions in the form of vectors, and implicitly this is this. If you want to be just, this is the x and this is the y. But yeah, this is not very important. This is perfectly okay, but we're not over. So for we have just one case left. We assume that 1 plus t is equal to 0, namely t is equal to -1, then from what? From this passage, let me write it as a star here. We obtain okay, 1t1, and this is 0, 0, -1. Well, t is equal to -1, so this is it. 0, 0, -1. Let's write this -1 a little bit better. Okay. We conclude. This you can conclude immediately because I mean you know the theory that in this case Vt is equal to the empty set, and this is it. This is a properly written solution. Well, perhaps my handwriting is not so good, but this is going to be perfectly accepted and very detailed. You see that everything you do, you say it. You detail every step. You make some cross references if needed. Example here. And yes, you also do some computations here, and you express your solutions like this. In that case here, and in the other case here. So this is okay. Let's do this for the second one, which is probably a little bit, I mean, systems are kind of boring because there are some computations involved, but yeah, but the next exercises are going to be a little more conceptual. Oh, okay. So let's put another page here. Okay. Okay. Here we just have to like to give some names. This is the important thing. So let's do this. The production matrix perhaps production is not a very good name. I mean the matrix, this matrix, I want to give her a name. How can I call it? The production matrix or the processing matrix? Well, let's say industrial processing matrix. Let's see, defined as follows. According, well, handwriting, according to the data. Okay. How do we call it? How do we call it? M? Yeah, why not? Very not really fancy name, but yeah, we call it M. And just to be very clear, I'll put again this is kind of important because it expresses how you organize your data here. So here in input you have kilo of plastic. Here you have kilo of copper. Here you have liter gasoline. And here you have this was orange, yes. Here you have what? One plastic pipe. One, well, okay, and here is one copper pipe. Okay, fine. So let's put the numbers in. So 2, 0, 0.3, 0.50501, 0.1, 0.304. Okay, good. Sorry, here, fine. Okay, and then we have two other matrices. The expected production matrix is defined as follows. Okay, so yes, let me call it P. Again, here you have this like generic output, which, I mean, this is not really necessary. Well, perhaps just put it a little lower here, okay. And important thing is that here you put your plastic pipes, rolls of wire, and copper pipes. Okay, and then you put numbers in, namely 800, 420, and 680. Okay, here, and this is it. And finally, the costs matrix is defined as follows. Okay, let me call it C. And now this is, yeah, so remember, this is euro here, and here you have the red thingies. So this is going to be kilo plastic. Handwriting. No one will be failed for handwriting. Because I had to, if so, I would have to fail myself. Okay. So you put your data here. What is it? 100, 210, and 50. And this is it. So we can finally, we've given names. So one, your answer directly. So what is the, sorry, that was A. Well, sorry, that was A. The total amount of materials needed for the desired production, the expected production, is given by, and you have to do this matrix multiplication, but since we put names, then it's very easy. So it's just PM. And just to be very detailed, you break it down like this, and this is going to be, and you just like, this is going to be kilo plastic, kilo copper, and liter gasoline. This is not really necessary, but I mean, but just to be really detailed. Okay. And finally, to answer the second one, the production costs in euro are given by the product PMC. Even in line PMC, and this is it. I mean, it's here for this exercise. It's not really important to do computations, because I mean, they are numbers. They're not so important. But it's like just important to write this kind of things, so that it's very clear what you're doing and how you get to the result. And then, I mean, the computations here are not actually essential. Unfortunately, they are for the linear system, because you have to go through them to find the solutions. Of course. I mean, if you make some computational mistake, this is going to be considered a minor error. It's not going to be a bad error. I mean, a bad error is something like you forget to to distinguish cases, and this is bad, of course, but not if you just exchange a plus and a minus and something like this. This is not important. This is not really a bad error. And I mean, here unfortunately you have to do computations and to be careful about them. But here, in this case, it's not important. So you can just write this. It's important here. What I want perhaps to remark is give names. So I call this M, P, and C, and then you can write it PMC without having to copy it again and again, and you know that this solves the problem. Okay. Yeah, this is it for the second one, and the third one is perhaps the most interesting, perhaps for myself, because I'm like a mathematician. So okay, let's do this, and let's write a detailed proof for each of these claims. For one, let's just start declaring the claim is true. Indeed. Wait. Oh, sorry. Indeed. And then for any square matrix A, we have A plus A TR. Was it? Yeah. TR is equal to A TR plus A TR TR. And here, if you want to, is equal to ATR plus A, and is equal to A plus ATR. I mean, this is perfectly acceptable. If you want to be even more detailed, you can put some like notes. For example, here you can say transposing is linear, and here you can say TR is equal to A. It's not really essential, but yeah, if you're writing something for like someone which is let's say if you want to give really all the details for yourself, or yeah, for whomever is going to read this, then yeah, it's nice. It's like an even more guided proof, but it's not really essential. I mean, here you're using some known facts, and the known facts from your theory, you can always use them without any problem. Yeah, of course, as I said, it's up to you if you want to be a little more detailed or less more detailed, but you don't be, if you don't like to, you don't really have to be excessively detailed. But if you instead you really like to give any detail and to be like really write everything, then you can do it. I mean, it's up to you. You can choose whatever you feel better with. So, and also another thing, you can also put this sentence at the end. So you can say, for example, for any square matrix A, we have etc., and then and you can conclude. Then, or perhaps better, for any square matrix A, we have this, and then you write, hence the claim is true. And again, this is up to you. You can either put put this as a third sentence or put it later. I mean, the point is not how you actually organize this. You have some freedom, of course. The point is that you should be satisfied with what you write, and you should think, what about people reading this? Is this clear? Is this sufficiently detailed? Is this nicely written? And then you make adjustments depending on how you feel about it. Okay, so let's go on. And for the second, just changing the style just to show. I'm just changing the style a little bit just to show you some possibilities here. You can also start with let A be any square matrix. Then, and you do what you have to do. So this is the product. ATR TR. Is it? Yes. So here, yeah, you transpose the product by switching. So ATR again TR, and then ATR, and then this is again ATR. So hence the claim is true. Okay. I mean, I didn't put the extra details like this, but if you want, you can do it. You can do it, of course. So the third. Let's say this. The claim is false. Is false. Indeed. If A, this is the counterexample. So we decided that this was a good counterexample. We have A minus ATR. So what is this? 0, 1, minus 1, 0. Is this correct? I think so. I think so. Which is not symmetric. Handwriting. Symmetric. I mean, if you the fact that that this is not symmetric, given that it's really so explicit, you can stop here if you want, because I mean, you can assume that who reads it knows by just looking at this matrix, it immediately sees that it's not symmetric. You're assuming that the reader knows how to transpose things. If you don't want to assume this, and you want really to, and you really want to be extremely detailed, then you can like add some more explanation here. The transpose between parentheses, if you want, the transpose of 0, minus 1, 1, 0 is 0, minus 1, 0. Well, sorry, 1, 1, 0. Okay, and this is like an extra explanation, but it was up to you. I mean, you can assume that the reader knows how to transpose matrices. And I mean, as you see, it's really, in this case, it's as I already said, you have some freedom. It's up to you to decide. But the point is, what you should have in mind is like really, you want the reader to have a nice experience. Let's say this: the reading experience has to be as nice as possible, as clear as possible, and as detailed as possible. Let's also say this. And yeah, normally I'm not against a lot of details, but you can, as I said, you can choose if you think that some details are not essential, and the solution is even nicer without being like too pedantic, then you can try and remove them. But be careful that they are really not essential details. So when in doubt, I think it's better to be pedantic than not. If you give more details, the reader can say, yeah, well, he's giving so many details, I already know this, but the reader can skip. Whereas if you forget to make an important point and to give an essential detail, then the reader is there and they think, well, what now? What am I supposed to think now? Why is the solution like this? Why after this passage then comes this one? I don't understand it. I don't see it. I don't get it. And this, of course, makes the experience worse. And this is what you want to avoid. The goal, really. Just keep this in mind. Imagine that you're going to read this after a while, and then think: is this something I would like to read or not? Just try to answer yourself these questions while you write down these like nice solutions. Okay, so yeah, that was enough for this like lesson. So yeah, see you